All right, let's take a look at one more type of example with trig substitution because we've already done an example where we had our perfect square minus x squared underneath our square root. And we've also looked at x squared plus a squared. So now let's take a look at this last example where we've got our x squared minus our perfect square. What's nice about this one is that our perfect square here is 1. That's going to make things a little bit easier. But when we have this situation, how we're going to set up our triangles, we're going to put theta there, and we're going to make x our hypotenuse, 1 our opposite side, or our adjacent side, excuse me, and then x squared minus 1 is going to be the opposite side in this case. So again, we do this because then x is going to be, or x over 1 is going to be secant of theta. So x is going to be secant. That's why it's kind of nice that a is 1 in this case. That the square root of x squared minus 1 over 1 is tangent of theta. Again, we're just getting these from our regular trig ratios, opposite over adjacent, and secant is 1 over cosine. So, they're not coming from anything we don't already know. And then we always, again, take this one where we have x is equal to secant of theta or whatever trig function we get. This we want to take the derivative of both sides. Here we get secant of theta, tangent of theta is equal to d theta. And so these three relationships here are what we're going to possibly use in our integral to get rid of all of our x's and have them all in terms of theta. So let's rewrite our integral. So x squared minus 1 over x dx. So looking at all of the pieces here, so the square root of x squared minus 1, that's equal to tangent. So that's going to be on the top of our fraction. X is secant of theta, so that's going to be on the bottom of our fraction. And then our dx is secant of x tangent, or secant of theta, tangent of theta, d theta. Ooh, I'm replacing so much there. So secant of theta, tangent of theta, d theta. So now our integral is all in terms of theta, and there's a little bit of canceling that we can do. So maybe like we did in the last video, we will copy this before we cancel it, so that again we can see that sort of original substitution that we have before we kind of clutter it up with canceling here. So we have a secant on the top of the fraction and a secant on the bottom, so those do cancel. And then this is also equal to the integral now of tangent squared of theta d theta. So tangent squared, I don't know what the integral of that is, but I do know that tangent of squared of theta is equal to secant squared of theta minus 1, and I know the integral of secant squared. So I'm going to replace my tangent squared with secant squared of theta minus 1 d theta. So remember, the integral of secant squared is tangent. So our secant squared of theta turns into a tangent, and then the integral of 1 is theta, because theta is our variable. So we got our integral. That was the whole point of us doing this sort of kooky trig substitution. And that's the point of any type of substitution that we're doing, whether it's our more standard type of substitution or this kind of crazy looking trig substitution. We're always trying to get our integral into a form where we know how to take the integral. And so now we have to kind of go back and substitute back. So back up here, underlined in green, we've got the tangent of theta is that square root of x squared minus 1. So that we can deal with right away. This plain old theta, so where we go, what do we do with that? So what do we do with this? Well, theta is the angle in this triangle, and sort of the simplest relationship between our x variable and theta is secant here. That x is equal to secant of theta, and if we use our inverse functions, that the inverse secant of x, that's going to be equal to theta. So we can use that and plug that right into our answer. And so we're going to get the square root of x squared minus 1 minus inverse secant of x plus c.